Hello, my name is David Karoly and I'm the leader of the Earth Systems and Climate Change Hub in the National Environmental Science Program, and I'm going to be giving a brief overview on observed and projected changes in the mean climate as part of this briefing session for the government review of the IPCC Sixth Assessment Report, Working Group 1 report. I've only got to about 14 minutes or 15 minutes to go through, so I'm going to cover things fairly briefly. And I'm going to start off with the observed climate change, and the clearest indicator of the observed climate change is the changes in global mean temperatures on a year-to-year basis. And this image shows the changes in global mean temperature from 5 different analyses or data sources relative to the pre-industrial period, or the average from 1850 to 1900. We can see the temperature scale on the left-hand side, and 0 therefore is the average from 1850 to 1900. And across the bottom is the time scale starting in 1850 going right up to 2019. You'll see a dashed line close to the top, and that marks 1 degree Celsius above pre-industrial times. And we'll see that for the last 5 years, in fact, the average temperature is now above 1 degree C above pre-industrial levels, remembering that the Paris target for global warming is to limit global warming to below 2 degrees. And I'm going to be talking about the Paris target a little bit later on as well. But it's clear that there's been substantial year-to-year variability, as well as a pronounced warming over the last 120 years of about 1.1 degrees Celsius. And associated with that are many other different observed changes in the global climate system. And I'm not going to be able to show you graphics on all of these, but a quick summary is that, as I've said already, the most recent period of time, the last decade, is the warmest on observational record since 1850. Ocean heat content is a very important measure of the heat that's being accumulated in the climate system. And most of that heat that's been added to the climate system has been accumulating in the oceans. 90% of the extra heat in the climate system is actually accumulating in the oceans, and that ocean heat content has now reached record high levels in 2019. The warmer ocean temperatures, and particularly the warmer ocean surface temperatures, have also led to lower sea ice extent both around the Arctic, and Arctic sea ice has been declining substantially over the instrumental record, and sea level has also risen substantially, particularly due to warming of ocean waters, as well as melting of glaciers and ice sheet. And there's been a recent increase in the rate of sea level rise, primarily associated with increased melting in Greenland and Antarctica. So in 2019, we had the highest global mean sea level measured since we've had high precision altimetry records showing these sea level records. Let me now look at the more Australian climate changes rather than the global climate changes. This first graphic shows the variations in the rainfall over Australia, split into, on the left-hand side, the cool season or wintertime rainfall, but it's not just wintertime, it's the April to October average rainfall over the last 20 years from 1998 to 2017 as a decile or as a comparison to the all 20-year periods since the year 1900. And the color scales, the reds, the dark red shows record low rainfall in the most recent 20-year period compared with all other 20-year periods over the last 120 years. And what we can see is that the southwest of Western Australia and much of Eastern Australia either has much below average rainfall, shown with these orange colors, or record low rainfall, such as in southwest WA and in many parts of Victoria and the Queensland and coastline of southern Queensland and New South Wales. In contrast, what we've seen in the warm season, or October to April rainfall, is in fact increases in rainfall in the most recent 20 years compared with all the other 20-year periods. And in fact, much of Central Australia and much of the northwestern part of Australia has record high October to April rainfall in much of Western Australia, and particularly in the northern part of Australia, remembering that this October to April period is the essentially summer monsoon season. Now, we see these contrasts, and we often expect to see differences between the warm season and cool season rainfall, and that's exactly what we see in Australia, primarily due to changes in the atmospheric circulation. So while we would expect rainfall on average to increase in a warmer climate system, we only see that in the global average rainfall, and the spatial variations are very much affected by changes in the atmospheric circulation. And that's exactly what we see in Australia. Reductions in cool season rainfall in southern Australia, and in the warm season, increases in the rainfall in northwestern Australia. What about for now Australian temperatures? When we look at the temperatures in Australia, what is shown here are the annual average maximum temperatures averaged across the whole of Australia. And what we see for 2019 is a new record high annual average maximum temperature, now more than 2 degrees above the average for the 1961 to 1990 period. So again, these temperatures are departures from the long-term average. There's been a pronounced warming in the annual maximum temperatures as well as in the mean temperatures since about 1950. There's large year-to-year variability, but that year-to-year variability is now superimposed on a long-term warming trend with a warming of more than 1.5 degrees in maximum temperature over the last 100 years. And in practice, if you look at the average for the last 5 years, we've actually got temperatures now around 2 degrees warmer in maximum temperatures averaged across the whole of Australia for the last 5 years. So there is very clear indications of climate change due to associated with long-term warming, and many impacts associated with that warming. I'm now going to look at how well the observed temperatures compare with climate model simulated temperatures, and this has been done in terms of comparisons over the Australian region, as well as in model simulations over the whole globe. For the Australian region simulations, they're actually extracted from global climate models that provide data for the whole globe. But here what I show is a comparison of the Australian mean temperatures year by year in the wiggly line from 1900 right up to 2018. And then I've marked the 2019 temperatures, noting that these year-to-year temperature variations are for the mean temperature, not the maximum. That's why they're slightly different from the previous graph. The black line here is the 10-year average moving temperatures. And we can see that there's been a long-term warming trend in the mean temperature. We compare that to climate model simulations in these two, if you like, bands. The blue band is the climate model simulations just with natural variability, no increases in greenhouse gases or other human influences on the climate system. And it shows that with no human influences on the climate system, there is no long-term warming trend in the Australian model simulated temperatures. And in fact, the observed temperatures are way outside the model simulated temperatures since about 1950, since this warming trend in the observed temperatures. Now, if we look at a second set of simulations, and this is not simulations from one climate model, it's simulations from more than 40 different climate models that include the coupling between the ocean and the atmosphere, as well as now all of the human influences on the climate. And we can see that now there's excellent agreement between the climate model simulations that include the human influences on the climate, the increases in greenhouse gases and other human influences, such as increases in industrial particulates or aerosols. And we can only explain this observed warming in climate model simulations that include these changes in the human influence on the climate, particularly the increases in greenhouse gases. We can also see in the red band, which is the projections beyond 2020, that we expect an ongoing warming in the climate system for at least the next 10 to 20 years or so. And what I'm going to do now is look at the model projections into the future as well. This graphic shows lots of comparisons of climate model simulations, for instance, for global average surface temperature, between high emission scenarios where what is used to drive the climate models is estimates of the increases in greenhouse gas concentrations in a high emission scenario, and in contrast in a low emission scenario. And what we find for a low emission scenario in these older climate model simulations, a reasonably good chance of global temperatures remaining below 2 degrees Celsius above pre-industrial levels. Whereas for the high warming scenario, we get increases in global temperatures of about 4 degrees. And it's important to see here that the zero line is not pre-industrial levels. The zero line here is the average temperatures in the period from 1985 to 2005. So it's essentially this last 20 years in the observational period. What we do know is that to actually estimate the future temperatures relative to pre-industrial, we have to add about 0.6 of a degree to those temperatures. What this graphic shows is a range of different impacts projected into the future, as well as the past variations, for instance, in the number of marine heatwave days, the reductions in the Arctic sea ice extent, which I said had already been falling. And what we see is that by around 2050 to 2100, there is, in the model projections, essentially zero Arctic sea ice extent in September. There are a number of other impacts from the increases in carbon dioxide in the climate system, including increases in the acidity of the ocean, which gets much more dramatic for the high emission scenario. So under the low emission scenario, ocean acidity stabilizes because the carbon dioxide concentrations stabilize, but in the high emission scenario, the ocean pH, the ocean acidity continues to worsen and has major impacts on marine ecosystems. Those are the summaries of the, if you like, mean climate and projected climate change. But I'm now going to talk about, for the next 3 or 4 slides, a set of new climate model comparisons that have been undertaken as part of the new generation of coupled climate model simulations undertaken both in 2019 and in 2020 as part of the Coupled Model Intercomparison Project, an international project that coordinates standard climate model simulations. And what I'm going to do initially is essentially to show you one set of metrics, in this case, the Australian mean temperature, relative now to 1995 to 2014, compared with the observations up to 2020, and then showing how well it progresses into the future in 2 sets of comparisons. There is the previous generation of coupled model intercomparisons called Phase 5 of the Coupled Model Intercomparison Project, which was completed in 2015. And the new phase of the Coupled Model Intercomparison Project, which is essentially underway at present and is still being completed. What I'm showing you is in the lighter grey and then the darker region, which is overlapping, the coupled model into comparison project phase 5 and the temperatures shown in that for Australia, in contrast to the new CMIP6, which are the darker grey range. And what we find is that the new climate models are showing enhanced warming over Australia because many of these models show a higher climate sensitivity relative to the same greenhouse gas emissions. For global temperatures on the right-hand side, there are two histograms, the older CMIP5 and then the newer CMIP6 simulations shown as histograms, and what we find is a pronounced higher warming in 2100 for global average temperatures. Not all the models show higher warming, but about 30% show substantially higher warming, not only for the global temperatures, for the annual temperatures, which means that it may not be appropriate to use the CMIP5 model projections to understand the likely impacts of climate change for a given greenhouse gas increase scenario relative to the future. There are now estimates of the sensitivity, what's called the equilibrium climate sensitivity for a doubling of carbon dioxide. In the last IPCC assessment, the likely range was estimated to span from 1.5 degrees to 4.5 degrees. And now we find that more than a third of the new climate models have warming greater than the 4.5 degrees Celsius likely range, and none of the models have warming or climate sensitivity which is less than 1.5 degree. In other words, there's now substantially higher warming that's possible in about 30% of the climate models for exactly the same scenario. In this case, a scenario of stabilization at doubling of carbon dioxide. This is critically important to understand in terms of the future sensitivity of the climate system, as well as the impacts of warming, because what it may mean is higher warming for the same future scenarios. The other important change that's happened is a renaming of the greenhouse gas emission scenarios to be called shared socioeconomic pathways. They actually use the same greenhouse gas emission scenarios as was used in the last IPCC assessment, what were called representative concentration pathways, or RCPs. And those RCPs are shown on the right-hand side of this graph along here. But these RCPs are now called shared socioeconomic pathways, and they include, if you like, socioeconomic changes that go with the emission scenarios. Let me now show you simulations just with the Australian Access Community Climate Model. These are two different sets of simulations for two different scenarios. And the interesting thing is that the ESM 1.5 or Earth System 1.5 model has a lower climate sensitivity of around 3.8 degrees, and the CM2 climate model, the coupled model version 2, has a higher climate sensitivity. And we can see that if we look for this SSP 5-8.5 or the high emission scenario, the RCP 8.5 scenario, we can see that this model, the Access CM2 model, shows higher global warming by about 1 to 1.5 degrees in 2100 relative to the ESM 1.5 simulations. And the ESM 1.5 simulations are consistent with the, if you like, previous CMIP5 simulations. And this clearly shows that the new models, with improved representation of many processes in the climate models, including cloud processes, seem to show, in many cases, a higher sensitivity to increases in greenhouse gases. We can see the same thing in the low warming scenario, that in this case, the Access CM2 climate model does not stabilize temperatures at below 2 degrees with respect to the 1961 to 1990 levels, or even with respect to the pre-industrial temperatures. In fact, this model, the Access CM2 with the very low emissions, has global average temperatures of around 2.5 degrees above pre-industrial levels, and it doesn't meet the Paris objective of limiting global warming to 2 degrees. So let me finish up now. Just to summarize, what it is clear in the IPCC assessment and in the peer-reviewed publications, that we are seeing a continued observed increase in global climate change associated with global warming, increases in ocean heat content, increases in sea level rise, and declines in sea ice around both the Arctic and the Antarctic over the last 5 years. Projections of future global warming of around 2 degrees occur in all the emission scenarios by around 2040 in time, with very little dependence on the different emission scenarios. But when we look beyond 2040, we see much larger differences in both global warming and in the impact on the climate system, dependent upon the future emission scenarios. The apparent differences in warming occur only after 2040, but the emission reductions need to occur from 2010 onwards. And global emissions need to peak well before 2020 if we're to achieve the stabilization of temperatures at well below 2 degrees Celsius. Importantly, some new climate model projections show higher climate sensitivity and higher rates of projected global warming for the same emission scenarios, and about 30% of the new models show this higher climate sensitivity and need to be taken into account to better assess whether it's possible to limit global warming to well below 2 degrees, the Paris Agreement. I have included a set of references, and if you've got any questions, please send me an email and I will endeavour to answer your questions. Thank you very much.